We have begun considering circular motion, rotational motion, and the simplest aspect of that is uniform circular motion. We will also, for this unit, and have been, considering centripetal acceleration. It's related to uniform circular motion. Uniform circular motion is just motion in a circular path with a constant radius and a constant speed around the circle. So that constant speed around the circle, if you were to clock it at any position, say this one over here on the right side of the circle, if you were to clock it just as the object came along there and clock it as if it were coming straight at you here in this position, it should give the same speed as if you were to clock it when it got to this bottom position on the circle coming straight at you if you were at the left of it. And likewise, if you're straight up above this leftmost position on the circle, when the ball was coming around and hit that point, it would be going the same speed as it had been at these other 2 points we considered. And likewise, if we were out to the right of this topmost position, we would notice it we would clock it as having the same speed as if it was coming straight toward us out there to the right as it had been going in all those other positions. But all those other positions technically are different, result in different velocities. It's all the same speed all the way around, but of course a different direction makes a different velocity. A velocity vector pointed in a different direction is a different velocity. So the velocity is continually changing, but only changing direction. Its magnitude, its absolute value, is the same all the way through. And that's what we mean when we say its speed is unchanging. So this is uniform circular motion. The radius of the circle is not changing. The speed of the object traveling the circular path is not changing. We'll again see that we've got the constant speed on a circle of a fixed radius, and we're gonna say that we're gonna define that speed that never changes in uniform circular motion. We're going to define that as tangential velocity. That's because it's at a tangent to the circle. The tangent to the circle is perpendicular to the radius, and so at any point along here, if you were to clock it as it reached that point, the object speed would be at a tangent and it would be constant. So we represent tangential velocity with the symbol v subscript t, although on your AP formula sheet it will not have the t down there, but I commonly write that on the board when I'm talking about this because I want you to distinguish it from just plain old velocity in a fixed direction, never changing direction. So this is tangential velocity, where the velocity is a new velocity at every moment because the velocity is directed in a different direction every moment as it goes around this circle. So we call it tangential velocity, but really in a sense it's just a speed that's never changing, and it's directed at a direction perpendicular to the radius of the circle. Well, what keeps such a thing on a circular path? What keeps an object going in a circle? It's called centripetal acceleration. This is not to be confused with the idea of centrifugal, which is a wrong concept for anything related to circular motion. Centripetal acceleration, that means acceleration, well, acceleration first of all is a change in velocity, right? So centripetal acceleration is a change in velocity toward the center of the circle, meaning it's only changing the direction, as we discussed earlier. The velocities that you see represented by just the four vectors we've shown in the four positions, and by the way, there would be such vectors at any position on the circle and at a tangent to the circle, which means perpendicular to the radius. Anyway, those vectors representing velocity are perpendicular to the acceleration upon them. The acceleration upon them is changing the velocity, not by speeding it up or slowing it down, but by redirecting it. So the velocity is continually changing direction because it's being accelerated, because the object is being accelerated toward the center of the circle. That's what keeps it on the circular path. Now notice I've tried to represent these acceleration vectors as being exactly equal in length or magnitude, but of course they're all at different directions. They're always changing. The acceleration on the ball is always toward the center, so it's a continually changing direction for the acceleration. Remember, acceleration is also a vector property, so changing the direction of an acceleration is to change the acceleration itself. It doesn't mean it's changing the amount of it. Well, we're going to define this as centripetal acceleration, so acceleration of an object toward the center of a circular path to keep it on a circular path. And when we've got uniform circular motion, which means there's no change in the radius, no change in the speed of the object around the circular path, when we have that, then the centripetal acceleration is a fixed amount. Now, it's changing direction continually, so it's like we're treating this as an absolute value of the acceleration at any time. But that amount, that absolute value, never changes if the circle's radius and the object's speed around the circular path never change. Alright, I want us to consider what would happen if suddenly the centripetal acceleration that we're not showing all the way around the circle, we just showed it at this one point here, but if it were suddenly cut off, if suddenly this ball is keeping a circular path because it's continually being pulled toward the center, if we just quit pulling toward the center on it, where would it go when it was released from any kind of other force and also from this centripetal force? If all the forces on it have canceled to this centripetal, to the force that's causing this centripetal acceleration, and if we then remove that force that's causing this centripetal acceleration, when we do it, where will the object go? So let's see. You see, it was directed downward at a tangential in a tangential direction, right? It was directed downward in a tangential direction just before its centripetal acceleration was removed, and therefore it continued in the same direction that it was already going in. This is according to Newton's first law: an object in motion stays in motion in the same direction with the same speed unless acted upon by a non-zero net force. So here we go. See? It just keeps on going in the same direction. Alright, we have a little formula for this unit. It's on your formula sheet. It does not, as I mentioned before, it does not have the subscript t here. It just says a subscript c equals v squared over r. So this is centripetal acceleration equals the tangential velocity squared divided by the radius of the circular path. And again, we're saying if it's a uniform circular motion, then the tangential velocity is constant and the radius is constant. And of course, that tangential velocity is just an absolute value. The absolute value of it's constant. And the radius's amount is constant, and therefore the centripetal acceleration amount is constant. And so it's a handy formula. We might consider, how do you figure out what the tangential velocity is? Well, before we get there, let me talk to you about something we call a period. This will enter into our calculation. The period we represent with a capital T because it's an amount of time. It's the amount of time for an object to complete one cycle. Now in this case, one cycle would be one full revolution around the circle, right? It would be the time it takes to go all the way around the circle and come back to the same point. That's one cycle. The time to complete that one cycle would be a period. And specifically, if we're talking about a circular path, then we could say that the time period, the period, which we represent with this capital T, is the amount of time it takes for one full revolution. A related concept is frequency. Let me back up here. A related concept is frequency. And frequency we represent with this lowercase f, and it is how many cycles happen in a certain amount of time. And I've animated this circular motion of this ball on the screen so that it will complete one full cycle every 4 seconds. So the period that we would have been talking about would have been 4 seconds per cycle. But here we're saying, or 4 seconds per revolution. Here we're saying how many revolutions can it make in a second? Well, it can't even make a full revolution in a second if it's taking 4 seconds to complete a revolution. So it would be a quarter of a revolution per second, right? Anyway, since in this case with the circular motion, the cycles we're talking about are complete revolutions starting at one point and coming back around the circle to the exact same point, we could say frequency is the amount of revolutions per time, and of course in physics we measure time in seconds. And you can see then that the period is just the reciprocal of frequency, and that the frequency is just the reciprocal of period. It's a very easy relationship.